based on this variation for finding molar mass of a gas, we know a couple things about the conditions that this gas is under. STP means that our pressure is what? 1 atmosphere, and our temperature is 273 Kelvin. Right? What do we also know about the molar mass of F2? Right? It's 38. So molar mass of fluorine is 19, and since there's 2 of them, molar mass is really 38 grams per mole. Okay, so yes, you need to do that math on your own, but that's kind of mental math, okay? And then we know that R is equal to, good, 0.821. And we want to find density, right? Easy peasy. So 1 atmosphere times 38, oops. Now we're going to move on to something called Dalton's law of partial pressures. Dalton's law of partial pressures. So all it says is that if we have a mixture of gases in a container, you find the pressure of each individual gas, and then you add them together. Okay, that would give you the total pressure of the system, right, of all these things mixed together. Okay, it could go for as many gases as we have mixed together, right? If there's just 2, it's just P1 plus P2. If there's 17, it goes all the way up, right? It's just an addition of those partial pressures to give us a total pressure. Right, if I have two individual containers, one contains this blue gas, one contains orange. Each of them has a certain pressure, which means they're moving at a certain speed. There's so much force applied over a certain amount of area. And so when you combine them, you just get that sum of pressure, right? It's not a really difficult concept. It's just you have to maybe do a little bit of work depending on how many gases there are. Okay, so let's look at this problem. Consider the following apparatus containing helium at both sides at 45 degrees. Initially, the valve is closed. When the valve is opened, what is the pressure of the helium gas? Okay, when the valve is opened, what's the pressure of the helium gas? So we've got 2 separate containers to start of helium gas, right? And we open the container. Now we have 1 container of helium gas. Okay, they each are containing different pressures to start, and then we're going to look at the final pressure at the end. So we're going to work these basically individual, and then we'll add them together. So the first way you can use this would be with Boyle's law, which is P1V1 equals P2V2. So we're going to basically look at what happens after that valve is opened, both on the left side and on the right side. Even though it's the same gas, right? On the left side, My initial pressure is 2. My initial volume is 9, right? Do you see what equation I'm using? P1 V1 equals P2 V2. Right? Initially on the left side, my pressure is 2 atmospheres, 9 liters. After the valve is opened, I want to find out what's the pressure on the left side, right? It's still going to be one container, but we're just looking at what's happening to this yellow helium gas after the valve is opened. So what's my new volume after the valve is opened? 9 liters plus, right? My new volume is 12 liters because this yellow gas can now start streaming into here, right? And the green gas will start going this way. Does that kind of make sense? Right? They have the whole volume now open to them. So I want to find out what's the pressure of that yellow helium gas after the valve is opened.
Where does the 12 come from?
The 12 comes from the addition of the volume on the left side plus the right side.
Why don't you do anything with the right side?
We're going to do that next, and then we'll add them together. So we're going to find what's the final volume of the yellow gas and the final volume of the green gas, and then we'll add them. That'll be our partial pressures. Okay? So that gives me 18 equals P times 12. So P equals what, 1 1/3? No, 1 1/2. 1.5 atmospheres. Okay, are we on the same page with that? After the valve is open, this yellow gas, we're not really concerned that they're both helium, right? That doesn't really affect the problem at all. But the yellow gas after the valve is open now has more room to roam. So pressure of the yellow gas afterwards 1.5.
So why did it go down?
Because there's the same amount of force applied over a bigger area. So when your denominator would get smaller, your answer would get bigger. Does that make sense? So same amount of force, you just have more area to roam.
So you divide the second pressure by the first pressure? Or how you divide?
How did I get 1.5? 2 times 9 is 18 equals P times 12. So I took 18 divided by 12 equals P. This is P1 times V1 equals P2 times V2. That's Boyle's law. I'm going to do the same thing on the right side. So my initial pressure is 3 atmospheres. My initial volume is 3 liters. My final pressure, I don't know. My final volume is 12. So I take 9 equals P2 times 12. And P2 of the green gas is equal to 0.75. Yes? Okay. So now my total pressure of my whole system, P total, oops, sorry, I'm writing right in the bad spot. P total is pressure of the yellow gas plus pressure of the green gas equals 1.5 plus 0.75. Okay, so 2 gases mixed together, it doesn't make a difference to us whether, in this scenario, if they were the same gas or different gas. Right? We're going to look at another way to solve it here in a second, but you need to basically find out what happened to that yellow gas after the valve opened. Right? The volume changed. We want to find out what did that do to the pressure. Right? The number of molecules didn't change. The temperature didn't change. We just want to know, what did the volume change? How did that affect the pressure? Right? And we know that pressure and volume are inversely related, so if one goes up, the other goes down. Right? If we have an increase in volume, we should see a decrease in pressure. Okay, questions with that? All right. Let's try this one. Go ahead and take a second to get it written down. Or write down what you need, and then we will start working it out here in about 2 minutes. We know about the oxygen gas that volume. Our temperature, really, we don't want 25. We want it to be 298, right? 273 plus 25 is 298. So that's our temperature and our pressure. Okay, then our other gas, helium. Here's our volume. This is also 298, right? You can rewrite this however you want, but there you go. And then there's our pressure. Okay? We want to find out the partial pressure of oxygen, partial pressure of helium, and then we'll find our total new pressure. It's very similar to what we just did. Okay? So as I start looking at oxygen, I have an initial volume, I have an initial temperature, and I have an initial pressure. They were pumped into a system that has a final volume at a different temperature. So what equation can I use if I have all three of those components, a before and an after? What should I be using? The combined gas law.
So the temperature is the same on all of them.
Oh, you're right. You're right. We could use, because temperature is the same, you could use Boyle's law. That's right. Okay? Since temperature is going to be the same, 298 for all scenarios, you could leave temperature off. Good point. Okay? You don't have to. You could put in the 25. You're just going to multiply by 25 and divide by 25. So it's a wash. Okay? So oxygen has a... if I use Boyle's law. Pressure of 1.3, volume of 27.4 equals P2, which we don't know, and our new volume is 5.81. Right, everyone see where I'm getting those numbers at? The red is oxygen, right at the beginning, so 27.4, 1.3 atmospheres. Both of these gases started out separate, and then they were put into a new container that had a volume of 5.81 liters. So we want to find out the pressure of oxygen only in that new container. Okay, so this is oxygen only. In the new container has a pressure of 6.13 atmospheres. If I'm looking at helium, it has an initial pressure of 2 atmospheres, an initial volume of 8.5 liters. Final pressure we don't know, and final volume we know is also 5.81. So with oxygen, our volume decreased, so our pressure increased, right? Is the same thing going to happen for helium? Yeah, we're going from 8.5 to 5.8. So, yeah, we should still see an increase in pressure from the beginning to the end. So now if I need to find my total pressure, what do? I just add them together. That's it. Right? So I say 6.13 plus 2.93 equals 9.06 atmospheres. I'm going to tell you something about something called the mole fraction. Mole fraction is basically the number of moles of a single component divided by the total number of moles in the mixture, right? The number of moles of a single component over the moles total, basically. Okay, mole fraction is usually given by an X. N, remember, we know stands for number of moles, so it's saying N of some single substance divided by N total gives us the mole fraction. Will the mole fraction ever come out to be more than 1? No, the part can never be greater than the whole. Okay, so it's called a mole fraction for a reason. It should always be a fraction, right? Or in our case, a decimal, but it should always be a fraction. The reason this applies to us here is because since moles and pressure are directly related in the ideal gas law, we can calculate mole fractions using pressures as well. Okay, so you could take the pressure of one substance divided by the total pressure and get your mole fraction. Okay, so we're going to do a problem with that here in just a second. All right, let's try one. Partial pressure of oxygen was observed to be 156 torr, and the atmospheric pressure was 743 torr. Calculate the mole fraction of O2. So it really is as easy as it seems. For mole fraction, we take pressure of oxygen over pressure total. Is there a need for us to convert from torr to atmospheres? No, because they're the same units already, so there's no need for us to go through that extra conversion step. Okay? So all we would do is take 156 torr divided by 743. Oops. Torr. And we get a mole fraction of 0.2099. Now we're going to put a little bit more information into a partial pressure problem. So this is kind of partial pressures and ideal gas law and gas stoichiometry all kind of thrown together. So this one will take a few different steps to get to our final answer. So go ahead and write down the problem. I'm going to give you a minute or so to get it written down, and we'll look at what we need to be solving for. If you could turn to page 213 in your book, that's where this problem comes from, and there's a visual there that might be helpful for you to see. $213. If you don't have your book, it's not the end of the world. It gives you a visual of what's happening in this reaction. Because I left off a little part of the first part of the problem, and that'll make a little bit more sense with the picture. All right, so take a look on page 213, that figure 13, okay? The question says a sample of solid potassium chlorate, this guy, was heated in a test tube and decomposed by the following reaction. So here's our reaction, okay? In the picture above it, you can see that it's being heated in this test tube. The MnO3 is just used as a like a catalyst, so it makes the reaction go faster. It doesn't affect the reaction at all, but KClO3 is in the test tube and it's heated. It's releasing oxygen gas, which travels through that tube into that water bath and into that water holding system, and you see how the bubbles float up and cause that and cause that gas pocket at the top of the jar. Are you seeing what's happening there? That's how they're capturing the amount of gas that has been released, right? Because if you're burning something, how do you capture the gas that's released, right? Like this. So they have this oxygen that's being captured, and they measure that oxygen by the displacement of water. So if the jar was full, right, and now it's down 4 milliliters, that means 4 milliliters of oxygen has been put into that jar. Does that make sense? Okay, I just want you to understand what's happening in the reaction. Okay, so the oxygen produced was collected by the displacement of water at 22 degrees and the system had a total pressure of 754 torr. The volume of the gas collected was 0.65 liters, and the vapor pressure of the water is 21 torr. Calculate the partial pressure of oxygen gas and the mass of KClO3. Okay, so we're going to do partial pressure first. Partial pressure of oxygen gas. We were told that the total pressure, P total, is 754. Right? Are we on the same page with that? So that's all of our pressures of all of our things combined equals 754. Okay? We know that we have vapor pressure of water. So that means any water particles that are being heated in that jar and caused to evaporate, right, that causes vapor pressure. That's all that is, right? So if the water is getting hot enough for water to evaporate or vaporize, that's what vapor pressure is, right? There's a lot more that goes into vapor pressure, but essentially that's what's happening. If it gets water hot enough, we get vapor pressure. So we know the pressure of, I'll just put W for water, is 21. And we want to find out what pressure does oxygen gas have in that container, right? The only two things we have in that container are water or vapor pressure and oxygen gas. So if we say our total is 754, we know that's equal to the pressure of the water plus the pressure of the oxygen, right? We get that part? Does that make sense? So I would say 754 equals, let me write it again. 754 equals 21 plus pressure of O2, right? And then that's it. So we take 754 minus 21, and we get the pressure of oxygen is 733 torr. That will allow us now to start working with a gas stoichiometry problem. Because we want to know the mass in the sample. So we want to find out how many grams of KClO3 do we have. And the only thing we have now to work backwards is the pressure of oxygen. Do we see a kind of a sequence of steps that are going to help us get there? Any ideas? I will need to change torr to atmospheres, but what equation can I use to help me work toward a gas stoichiometry type problem? What'd you say? Yeah, the ideal gas law, right? If I know the pressure, the temperature, the volume of oxygen gas, I can find the moles of oxygen gas, and then I can lead to a stoichiometry problem. Does that kind of make sense? Okay, so I'm going to get rid of this bottom stuff here. And I know that my pressure of oxygen at that condition, 22 degrees Celsius, pressure equals 733. Okay, that is torr, but if we want to use the ideal gas law, we need to put it into what? Atmosphere. So I take 733 divided by 760. Okay, so that's my P. The volume of my oxygen gas collected was 0.650. The temperature of my system is not 22, but it needs to be 290.95. Good. I took 22 plus 273 to get it from Celsius to Kelvin. And then I always know my R value. That means I'm solving for the number of moles of oxygen gas. So let me do that in a different color here. Pressure was 0.964. V, 0.650 equals N times R times T. No, so now I have moles of oxygen gas, but I need grams of my reactant. So I need to do a stoichiometry calculation to get me from moles of O2 to grams of KClO3. So can I get rid of my work that I have here? Okay. So if I have 0.026 moles of O2, I go moles of O2 to what? Good. And where do these digits come from? The chemical reaction, right? So O2 gets a 3 and KClO3 gets a 2. Then I go moles to grams of KClO3. Moles here gets the 1. Molar mass always goes with grams. Bless you. I had about 122.5 for molar mass. Okay. So I double check my units. I've canceled moles of O2. I've canceled moles of KClO3. I'm left with grams of KClO3, which is what I want.